Welcome to RadOnc Smart Review Physics Edition.
Hey everyone.
We're jumping right back into the atom today, and specifically, we're heading inwards to the nucleus.
That's right. If you joined us for our previous session where we talked about atomic structure and, electron interactions, today we're focusing on the heart of the atom. And maybe more importantly, what happens when that heart isn't quite stable?
Right, because an unstable nucleus has excess energy, and
Mhm.
it needs a way to, well, transform into a more stable state.
And that process is radioactive decay.
Yeah, it's absolutely fundamental to so much of what we do in radiation oncology, from the isotopes we use in brachytherapy to, like, understanding shielding and everything.
Definitely. So today we're going to explore the different ways unstable nuclei undergo this transformation, by emitting particles or energy. Then we'll tackle how we measure the rate of this decay using concepts like activity and half-life.
Okay. And finally, we'll look at some really interesting scenarios involving parent-daughter decay, where one radioactive nucleus decays into another radioactive one, and how the relationship between their decay rates leads to these different types of equilibrium.
And look, this isn't just theoretical stuff. This is core knowledge you need for clinical practice every single day, and it's pretty much guaranteed to show up on your board exams.
No pressure, then.
Huh. So let's unpack this, starting with the different modes of decay.
Okay. So when we talk about the nucleus, we're talking protons and neutrons. And stability really depends on finding the right balance between them, right? There's that metaphorical line of stability on a chart of nuclids.
Mm-hmm.
And if a nucleus falls off that line, maybe too many neutrons, too few protons, or it's just too big overall, it's unstable.
Exactly. Radioactive decay is its way of getting back towards that stable line. It's a spontaneous process, and the key is understanding how each type of decay changes the nucleus. Specifically, its atomic number, Z, that's the number of protons, and its mass number, A, the total number of protons and neutrons.
Okay, so where do we even begin? There are a few different ways this can happen, maybe with the really heavy hitters.
Good place to start. Alpha decay, represented by the Greek letter alpha, alpha R. This happens in very heavy nuclei, typically those with a Z greater than, say, 82.
Okay, heavy guys. And what actually comes out in alpha decay?
The nucleus ejects an alpha particle. You can just think of it as a chunk, specifically. It's a helium nucleus, two protons, two neutrons, all bound together.
Ah, okay. So if you're kicking out two protons, the atomic number Z decreases by 2. Makes sense. And since you're losing 2 protons and 2 neutrons, the mass number A decreases by 4.
Precisely. A classic example is radium-226 undergoing alpha decay. Now, alpha particles are relatively heavy, and they travel only a very short distance in tissue.
Right.
But over that short range, they deposit energy very densely. That means they have a high linear energy transfer, or LET.
High LET, short range, got it. Okay, what about if a nucleus is neutron-rich? Too many neutrons. How does it stabilize?
That's typically handled by beta-minus decay, beta with a minus sign, Drosh. Here, one of those excess neutrons inside the nucleus converts itself into a proton.
Wait, a neutron just turns into a proton. That sounds like it messes with the charge balance.
It does. And to conserve charge and energy and all that, the nucleus emits a high-energy electron, that's the beta-minus particle, and also an antineutrino, which is a very, very weakly interacting particle.
Okay, so if a neutron becomes a proton, the atomic number Z increases by 1. But since the total number of protons and neutrons stays the same, right? One neutron gone, one proton gained, the mass number A stays the same.
That's the key point. When A stays the same but Z changes, we call that an isobaric transition.
Isobaric, got it.
And iodine-131, I-131, which we sometimes use therapeutically, is a classic example of a beta-minus emitter.
All right, so neutron-rich does beta-minus. What about the flip side, proton-rich nuclei? Too many protons.
Proton-rich nuclei have a couple of options. One is beta plus decay, also known as positron decay. In this case, a proton converts into a neutron.
Okay, proton to neutron, so that must mean the atomic number Z decreases by 1, and like beta minus, the mass number A stays the same again.
Correct. Another isobaric transition. And to conserve everything, it emits a POZ-itron, which is the electron's positively charged antiparticle.
An antiparticle, right?
And a neutrino, fluorine-18, F18, the isotope that's crucial for PET scans.
PET scans.
Decays via positron emission. That positron is key for PET imaging.
You mentioned proton-rich nuclei have a couple of options. What's the other one?
The main competitor to positron decay in proton-rich nuclei is electron capture, or EC. Instead of spitting out a positron, the nucleus actually pulls in one of its own orbital electrons, usually from that inner K-shell.
It snatches an electron from its own atom. What happens then?
That captured electron combines with a proton inside the nucleus to form a neutron, and a neutrino is also emitted here.
Interesting. So a proton turns into a neutron again, just like beta plus. That must mean Z decreases by 1 and A stays the same, another isobaric transition.
Exactly. Functionally, in terms of the Z and A changes, electron capture and beta plus decay do the same thing to the nucleus. However, electron capture leaves a vacancy in that electron shell it snatched the electron from.
Ah, right. And we talked about this before. When an outer electron drops down to fill that inner shell vacancy, energy is released.
Which we detect as characteristic X-rays or sometimes Auger electrons. This is why many brachytherapy sources like iodine-125 and palladium-103, which decay primarily via electron capture, are actually, well, they're effectively X-ray sources for therapy.
That makes so much sense. Okay, last one on the list. Isomeric transition, or IT.
Isomeric transition, yeah. This happens when a nucleus is already in an excited state. We call it a metastable state, or an isomer. This often happens after it's undergone another type of decay or maybe some nuclear reaction. It basically has excess energy, but isn't unstable in terms of its proton-neutron balance.
So it just needs to get rid of that extra energy without changing its identity, without changing Z or A.
Precisely. Z stays the same, A stays the same. No change in the actual nuclide. There are two main ways it does this. The most common is gamma ray emission, where the excess energy is released as a high-energy photon, a gamma ray straight from the nucleus.
Okay, just emits a gamma ray. And the other mechanism?
Internal conversion, or IC. This one's a bit different. Here, the excited nucleus transfers its excess energy directly to one of the atom's orbital electrons, usually an inner one, and just kicks it out of the atom. That ejected electron is called a conversion electron.
And just like electron capture, internal conversion leaves a vacancy in the electron shell, right? Which leads to characteristic X-rays or Auger electrons again.
You got it. And it competes with gamma emission. So, yeah, quite a few ways for these nuclei to get stable.
It's definitely a lot to keep straight, especially how Z and A change for each one. Do you have like a trick or a mnemonic to remember that?
I think a mnemonic helps immensely. Let's try this one, see if it sticks. Alpha. A drops by 4, Z drops by 2.
Okay.
Beta minus, Z goes up by 1, A is true. True meaning stays the same.
A is true, okay.
Beta plus and EC, Z drops by 1, A stays 2.
Z drops by 1, A stays 2.
High T, Z, and A. Nothing new.
Nothing new. Okay, let's recap. Alpha, A drops by 4, Z drops by 2, losing that helium chunk. Beta minus, Z goes up by 1, A is true. Neutron to proton, beta plus and EC, Z drops by 1, A stays 2. Proton to neutron. ITZ and A, nothing new, just releasing energy. And remembering beta and EC are our isobaric processes where A stays the same, that's also key. That's really helpful.
Thinking about how these nuclei transform, it always reminds me a bit of like trying to organize a super messy desk. Sometimes you have to get rid of a big pile of junk altogether that's like alpha decay, losing a big chunk.
Yeah.
Sometimes you just convert a messy stack of papers into a single nice labeled binder. Maybe that's beta minus, changing the form but keeping the total workload, the mass number A, the same. Sometimes you might swap a messy item for a more organized one. Maybe by pulling something useful out of a nearby box that could be electron capture or just kind of reformatting it like beta plus. And sometimes the desk is fundamentally okay. It just has this nervous energy, so you just shuffle things around slightly to feel better without really changing the contents. That's isomeric transition. It's all about reaching a lower, more stable energy state.
That's a great analogy, actually. It really is about getting to a more settled, lower energy state. Okay, so now that we know how they change, let's talk about how fast they do it.
Right, that brings us to quantifying decay and the essential equations we kind of live by in physics. The primary measure of how fast a radioactive sample is decaying is its activity, represented by A.
Activity, right. That's the rate of decay, simply the number of nuclear transformations or decays happening per unit time. The formal definition is A equals negative dN divided by dt, the rate of change of the number of radioactive nuclei.
But the most practical form, the one we usually use, is A equals lambda times N, where N is the number of radioactive atoms you have, and lambda is the decay constant.
Okay, A equals lambda N. And the units for activity are absolutely fundamental. The official SI unit is the BeK-ORel, abbreviated BQ.
BQ. 1 becquerel is defined simply as 1 nuclear decay per second. 1 per second.
But the traditional unit, which, let's be honest, you will see everywhere in the clinic, is the K or E, abbreviated C.
The Curie, yes. And you absolutely must know the conversion between them. This is non-negotiable.
Okay, me with it.
1 Curie equals 3.7 times 10 raised to the power of 10 becquerels.
Wow, okay, 3.7 times 10 to the 10th. That's a huge number.
It is. It's equivalent to 37 GIGU becquerels, or 37 GBQ. Giga means 10 to the ninth.
37 gigabecquerels. Okay, so to make it a bit more manageable, maybe in millicurie.
Exactly. 1 millicurie, written MCI, equals 37 megabecquerels, MBQ. Mega is 10 to the sixth.
1 MCI is 37 MBQ. Got it.
Yeah, you really need to get comfortable going back and forth between curies and becquerels and their prefixes like milli, giga, mega.
Absolutely critical. Now, the process of radioactive decay itself, for a large population of atoms, follows a very predictable exponential pattern over time. This is described by the decay law.
The exponential decay law.
Yeah. The number of radioactive atoms remaining at some time t, let's write it n of t, equals the initial number of atoms, n0, multiplied by e raised to the power of negative lambda times t. So nt equals ne.
NT equals NEL.
Okay.
And since activity is directly proportional to the number of atoms, remember A equals N. The activity follows the exact same exponential law.
Precisely. A of t equals the initial activity, A0, multiplied by e raised to the power of negative lambda times TAT. Same mathematical form.
Same form. Got it. Now, what about lambda, the decay constant itself? What does it represent? Lambda basically tells us the probability per unit time that any single nucleus will decay. It has units of inverse time, like per second or per day or per year. A larger lambda means a higher probability of decay.
No, it decays faster.
It decays faster, exactly.
This leads us directly to half-life, T1/2.
Right.
This is maybe the most intuitive way we think about decay rate, I find.
I agree. It's simply the time it takes for exactly half of the radioactive nuclei, or equivalently, half of the activity to decay away.
And the relationship between lambda and half-life is, well, you said it before, it's critical and frequently tested.
It is. Lambda equals the natural log of 2 divided by the half-life T1/2, or ON 2 rho.
Okay, ln 2 0. And the natural log of 2 is about 0.693, right?
Approximately, yes. So you'll often see that written as lambda is approximately 0.693 divided by T1/2. And of course, you can rearrange that. T1/2 equals the natural log of 2 divided by lambda.
TON 2 rho. Good. Then there's average life, sometimes called mean life,
Yeah.
symbolized as T sub A. What's that?
This is the average lifetime of all the radioactive nuclei in a sample. Yeah, considering the ones that decay really quickly and the ones that hang around for a long, long time.
So it's an average over the whole population.
Exactly. And T sub A is related very simply to lambda. T sub A equals 1 divided by lambda. T equals 1.
Ah, just the reciprocal of the decay constant.
Yep. And because of the relationship between lambda and half-life we just talked about, T sub A also equals the half-life T1/2 divided by the natural log of 2.
Okay, TUO is ln2.
Right. And using that 0.693 approximation for ln2, T sub A is approximately equal to 1.44 times the half-life T1/2. TO 1.44 times the half-life.
Okay, now this average life is really important clinically, isn't it? Especially for something like permanent brachytherapy implants, like prostate seeds.
Absolutely crucial. For a permanent implant, we often need to know the total number of decays that will ever occur from that source over its entire infinite lifetime.
Right, because that relates to the total dose delivered.
Exactly. That total number of decays is equal to the initial activity multiplied by the average life of the isotope. So for iodine-125 or palladium-103 seeds, T sub A is absolutely key to the total dose calculation.
That makes perfect sense. Okay, one more term here. Specific activity.
Specific activity. This is just the activity per unit mass of a radionuclide. So the units would be something like becquerels per gram or maybe curies per gram.
Activity per mass, why is that relevant?
Well, think about it. A higher specific activity means you need less physical mass, less stuff of the radioactive material to get a certain level of activity.
Ah, so you can make the source smaller, but still have it be very active.
Precisely. This is crucial for things like high dose rate, HDR, brachytherapy sources. You need a very, very high activity source that's physically tiny to fit into the treatment catheters. Isotopes with shorter half-lives generally have higher specific activity, which is why something like iridium-192 works well for HDR.
Gotcha. Okay, let's maybe try applying the decay law to a quick scenario. Suppose you're dealing with an iodine-131 source. We said that's a beta minus emitter. It has a half-life T1/2 of pretty close to 8 days.
8 days, yeah.
If you start with an initial activity, A0, of, say, 100 millicuries, what would its activity be 4 days later?
Okay, good example. First step is always find the decay constant, lambda, using the half-life. We know lambda equals the natural log of 2 divided by T1/2.
Right. So lambda equals ln2 divided by 8 days, and ln2 is about 0.693.
Yep, so lambda is approximately 0.693 divided by 8 days. If you punch that in a calculator, it comes out to about 0.086 per day. Those are the units, inverse days.
0.0866 per day. Okay, now we use the decay law for activity. A at time t equals A0 multiplied by e's raised to the power of negative lambda times t. We want A at time t equals 4 days.
Okay, so A at 4 days equals our initial activity, 100 millicuries, multiplied by E raised to the power of negative lambda, that's 0.0866 per day, multiplied by the time, which is 4 days.
Okay, let's see. The exponent is negative 0.0866 times 4, which is negative 0.3464. The days unit cancels out. Good. So A at 4 days equals 100 millicuries multiplied by e raised to the power of negative 0.3464.
All right, now you need E shrunk to the power of negative 0.3464 if you plug that into a calculator.
Let's see. It's approximately 0.707.
Okay, about 0.707, which means the activity at 4 days equals 100 millicuries multiplied by 0.707.
Which is 70.7 millicuries.
Yeah, exactly, 0.7 MCI. So notice, after 4 days, which is exactly half of one half-life,
Yeah.
the activity hasn't dropped to 50, right? It's dropped by about 30%, not 50%.
Right.
The exponential decay law gives us the precise value.
That walkthrough really helps solidify how to use that key equation. Okay, things get even more complex, and I'd say really interesting. When a radioactive nucleus decays not into a stable state, but into another nucleus that is also radioactive.
Ah, yes, the parent-daughter equilibrium scenarios. This is fascinating stuff. The relationship between the half-lives of the parent isotope and the daughter isotope it decays into dictates the behavior of their activities over time.
Okay, let's maybe start with the simplest case, where there's actually no equilibrium.
Right. That happens when the daughter's half-life is actually longer than the parent's half-life. So T1/2 of the daughter is greater than T1/2 of the parent.
So the parent decays relatively quickly.
Exactly. The parent produces the daughter, but then the parent disappears because it's short-lived.
And since the daughter lives longer, its activity builds up as it's being produced. But then, after the short-lived parent is mostly gone, the daughter just decays away slowly according to its own long half-life.
That's it. You never reach a state where their activities are linked in some stable ratio. The daughter essentially takes over and behaves like an independent long-lived source once the parent has decayed away.
Okay, no equilibrium. Got it. Next up is transient equilibrium.
Transient equilibrium. This occurs when the daughter's half-life is shorter than the parent's half-life, but not dramatically shorter. Think of it as T. 1/2 of the daughter is less than T1/2 of the parent, but maybe only by a factor of, say, 10 or 100, something in that ballpark.
Okay, so daughter is shorter-lived, but not way shorter.
Right. This means the daughter's decay constant, lambda daughter, is somewhat larger than the parent's lambda parent.
So the daughter decays faster than the parent. What happens to the activities?
Well, initially the daughter activity builds up from 0 as the parent decays. It actually slightly overshoots the parent's activity level for a while.
Overshoots it. Okay.
Yeah. But then, as the parent continues to decay, remember the parent have the longer half-life, its production rate of the daughter slows down, so the daughter's activity starts to decline. And here's the fascinating part. After a certain time, the daughter's activity starts to decay with the same apparent half-life as the longer-lived parent.
It decays with the parent's half-life.
It appears to, yes, because its decay rate becomes governed by the rate at which it's being supplied by the parent. But crucially, it maintains a consistently higher activity level than the parent. The ratio of daughter activity to parent activity becomes constant and greater than 1.
Okay. They decay in parallel on a semi-log plot, but the daughter line is above the parent line.
Exactly. The classic example here is the molybdenum-99 to technetium-99 meter generator used constantly in nuclear medicine.
The Moly-Techie generator, yeah.
Moly-99 has a half-life of about 66 hours, and it decays to Tech-99 meters, which has a half-life of only 6 hours. That fits the criteria for transient equilibrium perfectly. T's is less than TP, but not hugely less.
Right. So the Tech-99 meter activity grows in, peaks above the moly activity, and then decays with that apparent 66-hour half-life of the moly parent while staying at a higher activity level. That's how they milk the generator for the technetium.
Precisely.
Okay, finally, secular equilibrium. This sounds like the most stable long-term scenario.
It is. This happens when the daughter's half-life is much, much shorter than the parent's half-life. We're talking orders of magnitude difference. T, one half of the daughter, is vastly less than T, one half of the parent.
So the parent lives practically forever compared to the daughter.
Pretty much. This means the daughter's decay constant, lambda daughter, is vastly larger than the parent's lambda parent.
So the daughter decays almost instantaneously as soon as it's created.
Almost, yeah.
Yeah.
The daughter activity builds up very rapidly until its rate of decay is exactly equal to the rate at which is being produced by the very slowly decaying parent.
So decays equals production.
Exactly. At this point, the daughter's activity becomes equal to the parent's activity. A daughter equals a parent. And from then on, because the parent's half-life is so incredibly long, they appear to decay together, with the daughter activity tracking the parent's activity, both effectively decaying with the very, very long half-life of the parent.
They reach equality and stay there, decaying together very slowly. What's an example?
The textbook example is radium-226, which has that super long half-life of 1,600 years.
1,600 years? Wow.
Decaying down its chain to radon-222, which has a half-life of only 3.8 days.
Yeah, 3.8 days versus 1,600 years. That's definitely secular equilibrium.
Absolutely. Understanding secular equilibrium was historically vital when working with radium sources, because those short-lived decay products, like radon, quickly build up until their activity equals the radium parent's activity.
Okay, that clarifies the different equilibrium types. Stepping back, understanding all these modes, rates, and equilibrium states clearly has immense clinical relevance and direct applications in our radiation oncology practice.
Absolutely. I mean, just starting with isotope selection. The specific decay mode tells us what kind of radiation is being emitted. Is it alpha particles, beta electrons, positrons, which lead to annihilation photons, gamma rays, characteristic X-rays? This directly guides our choice of the appropriate isotope for a specific therapy.
Right. Are we wanting a beta emitter like yttrium-90 for liver mets or iodine-131 for thyroid, or are we doing brachytherapy and need sources like iodine-125 or palladium-103, which rely on those electron capture X-rays?
Or iridium-192 for HDR, which is primarily a gamma emitter. The decay mode dictates the tool we use.
And then there's source management. The half-life is just absolutely crucial. For high dose rate, HDR, brachytherapy, using a source like iridium-192, which has a relatively short half-life of about 74 days, we have to apply daily decay corrections to our treatment plans.
Yeah, the activity drops noticeably day to day. You have to account for it to deliver the correct dose.
Exactly. Conversely, for permanent implants like prostate seeds using iodine-125, T1/2, about 60 days, or palladium-103, T1/2, about 17 days, the total dose is delivered over the entire lifetime of the implant. And calculating that cumulative dose relies directly on knowing the average life T sub A of the isotope.
That T-euro calculation becomes central there.
And of course, safety and compliance. Being totally fluent in both activity units, curies, and becquerels, and knowing that conversion 1 curie equals 37 gigabecquerels inside and out is not just for exams. It's vital for handling sources safely, for documentation, and for meeting regulatory requirements. You can't afford mistakes there.
No way.
Yeah?
And those equilibrium concepts, while maybe less hands-on daily for most residents now compared to, say, HDR decay factors, they historically explained things like radium source behavior, and they still explain how radionuclide generators, like the Molly Techie one, provide us with these medically useful, short-lived isotopes on demand. It's foundational understanding.
Definitely foundational. Okay, let's try to condense this down into some core clinical pearls. These are the absolute must-remember points, especially as you're studying for your boards.
All right, pearl number 1. Know the decay rules. Got to know how Z and A change. Alpha, Z-2, A-4, beta minus, Z plus 1, A stays the same. Beta plus or electron capture. Z-1, A stays the same. Isomeric transition or gamma, Z same, A same. And don't forget beta decay and electron capture, those important isobaric processes. A stays the same.
Pearl number 2, activity. Know the definition decays per unit time and the units. SI unit, becquerel, BQ, 1 decay per second. Traditional unit, curie, CI. And that critical conversion, 1 curie equals 3.7 times 10 raised to the power of 10 becquerels, which is 37 gigabecquerels, 37 GBQ. Tattoo it on your brain. Seriously.
Pearl number 3, half-life versus lambda. Know that fundamental relationship. Lambda equals the natural log of 2 divided by t 1/2, which is approximately 0.693 divided by t 1/2. And be ready, really ready, to use the exponential decay law, AT equals AE area, for calculations.
Pearl number 4, average life T sub A. Remember, T sub A equals 1 divided by lambda, 1, that's the easiest definition, but also know it's about 1.44 times the half-life, T 1.44, T euro. And remember, it's key use for calculating the total number of decays, and thus total dose, from permanent implants.
And pro number 5, equilibrium types. Know the conditions based on the relative half-lives T daughter versus T parent, and the outcome for the activities A daughter versus A parent, transient equilibrium, TDTP, daughter activity becomes greater than parent activity, at AP, and they eventually decay in parallel, secular equilibrium. TD is much, much less than TOP, daughter activity builds up to equal the parent's activity, and they decay together with the parent's very long half-life.
Excellent, Pearls. You feel ready for a quick board review blitz? Let's see if those points stuck.
Okay, let's do it. Bring it on.
Question 1. An isotope undergoes electron capture. How do its atomic number, Z, and mass number, A, change? Is it AZ decreases by 1, A decreases by 1, BZ decreases by 1, A stays the same, CZ increases by 1, A stays the same, or DZ stays the same, A decreases by 1?
Okay, electron capture. A proton grabs an electron, turns into a neutron. So we lose a proton, meaning Z decreases by 1, but the total number of nucleons, A, stays the same because that proton was replaced by a neutron. So that's answer B. Z decreases by 1, A stays the same.
Correct. It's an isobaric process. Okay, question 2. A source has an activity of 10 curies. What is its approximate activity in gigabecquerels, or GBQA? 3.7 gigabecquerels, B, 37 gigabecquerels, C, 370 gigabecquerels, or D, 3,700 gigabecquerels?
All right, this is that conversion factor test. 1 curie is 37 gigabecquerels. We have 10 curies. So that's 10 multiplied by 37 gigabecquerels. 10 times 37 is 370. So 370 gigabecquerels. That's answer C.
Perfect. Nailed the calculation. Last question. In which type of parent-daughter equilibrium does the daughter's activity eventually equal the parent's activity? A, no equilibrium. B, transient equilibrium. C, secular equilibrium. Or D, both transient and secular?
Okay, daughter activity equal to parent activity. That happens when the daughter is super short-lived compared to the parent, so its decay rate matches the parent's production rate. That is the definition of secular equilibrium. So the answer is C, secular equilibrium. In transient, remember, the daughter's activity ends up higher than the parent's.
Excellent work. You aced the blitz. That really covers the key points.
Right.
So today, we really walked through the fundamental concepts of radioactive decay, exploring all those different ways nuclei transform and, critically, how that impacts their atomic number Z and mass number A.
Yep. And we looked hard at how we quantify that decay using activity, half-life, the decay constant lambda, and average life. We spent time on those crucial units, becquerels and curies, and the conversions you just have to know cold.
And we untangled the different scenarios of parent-daughter equilibrium, transient and secular understanding, how the relative half-lives of the parent and daughter shape their activity curves over time. It's quite elegant, really.
It really is a lot to keep track of, though, especially when you're cramming for an exam. Sometimes I feel like, my personal half-life for remembering physics details is about 10 minutes after I close the book.
Huh. Tell me about it. The struggle is real. Well, hopefully this review helps those key concepts stick around in your active memory a little longer than 10 minutes.
Fingers crossed. So next time, we'll move beyond the decay itself and look at what happens when the radiation that's emitted actually interacts with matter. We'll be covering concepts like linear energy transfer, LET, range, and the famous Bragg peak.
Sounds great. That wraps up this session on decay and activity.
Remember, you can find complete practice oral boards at RadOncSmartLearn.com. That's RadOncSmartLearn.com. And be sure to subscribe to RadOnc Smart Review for our next session.
Thanks, everyone, for tuning in.